the introduction, and I want to thank all of the organizers for the invitation to this very nice conference. Okay, I must say that I am not really a specialist in the formation of singularity and neither in general relativity. So I thought what I am going to talk about. And I thought that maybe what would be interesting is to talk, at least to define the Dirac equation on asymptotically flat manifolds. Okay, because it is something that has to do with Lorentzian geometry. And so somehow it is related to general relativity. And regarding the singularity, formation of singularity, okay, I will maybe not say much, but I will give you perhaps some perspective at the end of it. Okay, so if you have no idea what is the Dirac equation, don't worry, I will explain. You know what is an asymptotically flat manifold, so this will be okay, I think. And let me mention then and about Strichartz estimates. So you probably know that it is a dispersive estimates in say an average way over time for dispersive equations. In this case, for the Dirac equation. Okay, let me mention that this is a joint work with my collaborators, so Federico Cacciafesta from Università degli Studi di Padova and Longmeng from École des Ponts. Okay, so I will talk about what is the Dirac equation on curved space-time. Then I will perhaps tell you what are my assumptions, what I mean by, in this context, by asymptotically flat manifolds. Okay, I will present the result and then give some perspective, but mostly I will focus on what is the Dirac equation on curved space-time. Okay. So if you have no idea what is the Dirac equation, so let me tell you that a fancy way to say Dirac equation is to say relativistic quantum mechanics. Okay, so if you see a conference which is titled relativistic quantum mechanics, it means that they are going to talk about Dirac equation. Okay, so and there is something in the title, so it is both an equation from quantum mechanics and from special relativity. I will try to explain. So the history about it. That somehow we wanted to give a sense. Sorry, wanted to give a sense to equal MC2, which is the most famous equation of physics. Perhaps no, and so what it means in this context is just to give rise to the wave equation, but in the context of quantum mechanics. So or MU, what you want. And okay, so this is not an equation of quantum mechanics because, as you know, the equation of quantum mechanics are of this type with H, which is a self-adjoint. Okay, so what is the natural way to do this is to do this. IDT equals square root of minus Laplacian. Okay, so why not is that this is not an equation of special relativity because you cannot change your special relativity referential and have an invariant equation. And the point is that, okay, so what I will be more specific about it, but you have two types of invariants that you must respect in the context of special relativity. It is invariance by rotations and of space, and this is okay. But you have also to be invariant under what is called a boost transform, which is something of this type. So you're changing your time into, I guess this will recall some stuff. So into this. So you're mixing time and space. Okay. You're changing your one variable in this way. So this is x minus 18. So v is a parameter which is in 0, 1. And well, 0, 1. And gamma is just given by oh, why I said 0. 1 minus to the power 1 minus 1. Okay, and this mixes time and space, and of course, it does not leave this equation invariant. What do you do? So you say, okay, I have an equation of the first order, so I will write something. So I gamma mu, d mu. So okay, so I will introduce some mass m, which will be the mass of the particle. Okay, so what are the objects here? So here I have an implicit summation in both time and space. Okay, gamma are actually matrices. Gamma mu are matrices. So for short, so I'm in dimension 3. I would say that the result is not in dimension 3, or 1 plus 3. Okay, and what do you have then? So d mu are just the derivatives, and so u is some map, so which is from R. So 1 for time and 3 for space, which ends up in 3. And so the point is that if you put it up to the square, you want to get back the yes, maybe you have you want maybe to get something like this, and to if you put this equation to the square to get something like this, what you have to require on the matrices is the following, and it's that the anti-commutator of gamma mu and gamma nu is given by 2 times eta mu nu, where eta is the Minkowski matrix. Okay, so somehow this is okay. I mean, you can put you can write it as if you do a little bit of algebra, you can transform it in an equation of quantum mechanics. And if you put it to the square, if you have this this relationship, then you will find again an equation on scalar fields. So when the wave of Langevin equation of scalar fields. Okay, so M is some parameter. So what does it represent? It represents the free evolution of, so now I have been told by my physicist friend that I should not say a pair electron-positron, but a spin 1/2 particle when you have a, so it's a free evolution, so when it does not interact with anything. Okay. Okay, so that is the equation. So as I told you, it has to be invariant under the change of the referentials from special relativity. So what are those change of referentials? So changing the referential means so applying a transformation that preserves. So it should preserve the Minkowski matrix. And causality, the time orientation. So what is this? What are those transforms? So I mean, not necessarily. Those guys, if you consider only the linear transform that this is actually what you call the autochronous restricted Lorentz group, which I will write as L up, and which is so S node of N3 union with P. How did I write P? SO node of 1,3. So what is this guy? So this is just the connected components, the connected component of SO1 that contains the identity. And P is what is called the parity operator. And this is the operator that reverses the orientation in time. So it is this guy. So you have 1, 0, 0, and then minus the identity of this. Okay, so what is those groups? So if you look at what preserves the Minkowski matrix, so this is the group O of 1, 3. Yeah, and it has 4 connected. It has 4 connected components. One is this guy, so it is the one that conserve that contains the identity. So you have two things that you can do. So either you set the determinant to 1, so this will be SO13, or you set the determinant to -1, so this will be just the not SO13. And this is and then so sorry, I will manage it. And then what you preserve is not this. It's not SO13, so those are not the two components that you consider, because this would involve. So if you take the one which, if you do this, then you will break causality. But it is this guy and this guy, so it does not break causality, but somehow you include the fact that you have the right to change the orientation of your matrix. Okay, so of course, what I say is that the stupid remark is that this is a subgroup of O13 that of course preserves. Okay, so let me mention that this is maybe not all the transformation that you want to consider. So in particular, you need to consider the full Poincaré group where you will add the translation of the semi-direct product. So I say this for completeness, but this will not. This I will not be concerned by this. Okay. Okay. Okay, so now I will perform a change of variable in my equation here and check that it is still the same. So I do this. So x prime mu is just so L mu times x nu. So L is in my invariance group. And I will set from the beginning u tilde of x. This is just so u of ls. So if I do the change of variable like this, so I have my derivatives which will change a little bit, but not that much. And what I will get is that actually what I find is that I gamma mu d mu of u is actually equal to I gamma tilde mu d mu of u tilde opposed with L. So my new equation is there, where gamma tilde mu is given by just a linear combination of the original gamma mu, which is given by this. So you have to take your linear transform to the power -1 and then mu of gamma. Okay, so it is the same. So if this solves the Dirac equation, this will also solve the Dirac equation, but with a different set of gamma matrices. Okay. So what can I say about those gamma matrices? If I compute their anticommutator, this is what will happen. If I do this, so I will just I will just see the L's, the coefficient of L going out. So I will find this. So I will have, this will be, so L minus 1 mu rho. This will give you L minus 1 mu sigma. And then I have the anticommutator of gamma rho and gamma sigma. This, you know, it is given by the Minkowski matrix. So I have some 2, then L minus 1 mu sigma, mu rho. Sorry. Then I have eta rho sigma, and then I have L minus 1 mu sigma. Okay, but then you know that L minus 1, it is in this guy, so it is in particular in O of 1, 3. So this preserves the Minkowski matrix, and so you find indeed that you have 2 to the eta mu. Okay, well, so what does it tell you? It tells you that the new gamma matrices that you find, they solve the exact same anti-commutation relationship that you have for the gamma matrices. And now you probably remember that this actually sets a Clifford algebra, and that you have a complete classification of complex Clifford algebra. And so if you solve the same anti-commutative relationships, it tells you that the Clifford algebra are isomorphic. And in our case, this means the following. This means that there exists a mu of L, which is such that for all mu, you can rewrite gamma mu in such a way that it just becomes u of L, gamma mu, u of L minus 1. So you can do a change of basis that will transform your gamma into a gamma tilde. And this is all what it means. So you change your basis and you pass from one set to the other set. Now, what I mean is that really the u does not depend on u. Okay, so now if you look at what solves, I will maybe not do the computation or I will not have the time to say anything, but if you look at what solves this actually, so if u satisfies the Dirac equation, then what satisfies the Dirac equation is not exactly u tilde because you have to change your basis in C4, but it is a u of L, u tilde. Okay, so it is invariant under the change of, so it is covariant, so invariant under the change of special relativity referentials in this sense. So if you change your referential, somehow you have to change your basis in C4 for you. Okay, so there is no privileged basis in C4. This is natural. It is completely, it is driven by the referential that you choose, or the gamma matrices that you choose, if you prefer. Okay. What did I say? Okay. Yeah, I wanted to say what is U. Okay, before I say what is U, maybe I should say what is L up, and so to say this, I need to say what is S node 1, 3. So it is a group that is generated. So I have said this by rotations of space. And so-called groups. Okay, which are the one that I had written in the beginning, so which intertwine time and space. Okay, maybe I will not write this transform, but this is this. And actually, there are 6 generators of this group. So there are 3 rotations and 3 boosts. It is a group that's like this. And so what is U? So here you add just the parity. And so what is U? It is actually, so it is a map that depends on the transform that you consider in L up. So it is something that sends L up into a change of basis. So this is just in GL4 of C. Okay, and it's actually a group representation. By which I mean that it is only it is a group morphism, homomorphism. Okay, so if you have done a little bit of field theory, you know that they play an important role in the description of spins, for instance. Okay, so what I want to say is, yeah, I will make just some comments. So perhaps you know that you cannot have a finite dimensional representations of non-compact group that are unitary. So in particular, here I cannot replace GL4 by something unitary, but if I restrict my transformation to the rotations, then it is something that is unitary. And I just want to say one other thing is that U is not irreducible in the sense that you cannot cut it into small pieces that will leave invariant the space. but for SO node of 1,3, but it is irreducible if you add the parity operator. Okay, so the parity plays an important role in what you are describing. And what do I want to say more? This, then I will move. Yes, so then I just what do I want to add? This was it. Yeah, okay. So if you so now if you're taking the point of view of field theory, so of quantum field theory, you know probably that you can describe the spin by just looking at the representation of this group actually, and so that all the particles are well, the spin is defined by the irreducible representation of this guy, and so in this case. It is the irreducible representation of this guy in 1/2 plus another one in spin 1/2. Okay. And if you try to derive the equation that one particle which is like this satisfies, you will actually find the Dirac equation. So this is because the Dirac equation somehow was describing quantum field theory before we knew what quantum field theory said. And so it inspired this, and in particular, it is natural that when you know, take a higher point of view, you find back what the equation that you had originally. Okay, so what do I want to say more? I just want to say, what do you have usually for gamma matrices, just so that it takes some stuff, and you will see that it is related to spin also. So gamma naught, so the one that is acting of time, is just the identity in dimension 2 minus the identity in dimension 2. And the other, so the one that are related to space, they are actually given like this. They have something on the anti-diagonal. And what is on the anti-diagonal are actually the polymatrices. So those guys are the polymatrices that you perhaps know that they have to do something with spin. If you do not know what they are, they satisfy somehow the same anti-commutation relationship, but in lower dimension. And so sigma 1, I have not written them. Sigma 1 is, I think, I have to remember this. I think this one. Sigma 2 is the same between the I. And sigma 3 is 1 minus. Okay, so this is my also, and as I said before, if you put it to the square, then you find the Klein-Gordon or wave equation. And so what I want to do is dispersive estimate. So if I know some stuff about dispersion for Klein-Gordon of wave equation, which we know a lot about, then I will be able to say something about dispersion for the Dirac equation. Okay. Okay, so now let's move to a curved space-time background. So now I'm considering a manifold, okay, with a Lorentzian matrix. Okay, and I want to transform my equation in the Minkowski spacetime into an equation on this. So what do I do? Okay, I need to do an extra topological assumption is that you can use Cartan formalism, which means that there exists a matrix bundle. So in UA, such that it will connect your tangent space at each point with the tangent space of the Minkowski spacetime, which is this means that you have this. Okay, so this is a topological assumption. Actually, it is not a geometrical one. And what do I need to say about it? So now I will use Latin letters to say the Minkowski spacetime, and I will use Greek letters to talk about my Lorentzian geometry. Yes. Okay, so if you look at this, you will probably see that actually my choice of E is not unique, because you can change it by any guy in this game. So if I plug in U prime of mu A is actually L B A of E. You can do the algebra, it will give you some computation as there. And you will see that actually you also have that E prime mu A beta A B E prime mu B is also equals to G. So this choice is not unique. And actually, no, when we are going to consider covariance, we are going to say, okay, I want to have covariance, but I want to have covariance. But no, covariance means not I use a global transform, because this does not mean anything, but I will use a global, a local transform at this level. So at the level of this somehow sets the choice of frame you have for your tangent space. So I can choose, I can change my, change my tangent space with a Lorentz transform, and the physics will still be the same. So no, we are not considering covariance as a global level, but really as a local level. So what does the equation becomes? Yeah, I have written it. I will change it a little bit. So it becomes simply exactly the same. Because I gamma mu d mu is equal to m. U, of course, no, goes from your manifold to C4. And gamma mu, there are matrix bundles that you can write in the following way. So it depends on your choice of frame for the tangent space. Okay. And it depends on the algebra that you had for the Dirac equation earlier. So those are the gamma matrices that we had in the flat space. Okay, so you know this is a matrix bundle. So if you compute the anti-commutator of your matrix bundle, we know no longer find 2 times the Minkowski matrix, but 2 times your ambient matrix. Okay, this is just algebra. Okay. And so now what is d mu? It's a derivative, of course, but it has to be covariant. So it's a covariant derivative, but not only for fields, it is because otherwise it would be d mu is a covariant derivative for spinors. So it has to change. When you change the referential, it has to be invariant with the same way that the spinors are invariant. So I will write how it looks. We will not do so many computations, but it is just this guy. So you have the normal derivative, the usual derivative, and then you have 2 objects that describes it. One is purely geometrical. This is this omega mu AB. And it is what is called the spin connection. So somehow you can compare it with the Christoffel symbols. And this is purely algebraical. So I can write it down just to convince you that it is okay. So it is this guy. It's gamma A. Okay, so it depends. Yes.
Sorry. What are some examples of Lorentzian manifolds that admit such a matrix bundle, like compactly supported.
The one you want to use, I mean, synthetically flat manifolds.
So compactly supported, like a perturbation of Minkowski space.
Yeah, sure, this will definitely work, but even okay, I will maybe say something stupid, but I think if you have a manifold that will matrix that will solve the actual equation in a smooth way, then it will be okay.
Isn't this just the assumption that it's parallelized?
Yeah, that's it.
Yeah.
So like normal so like describing normal orthonormal basis at a given point on a smooth line.
Yeah, of the tangent space, yes, somehow. Yeah.
Same relation.
Okay, so this is purely algebraical. So this depends only on the particle you consider. So here we consider a spin 1/2 particle. If we had a higher spin, then the algebra would change, but not the geometrical path. It's completely related. So if you want to know what is this like, actually it is the generators of your group representation. So they are related to the derivative of your group representation. So somehow it is a basis for the Lie algebra that is describing everything. And so if you remember, I told you that there were 6 generators. So this matches this because it is a priori it has 16 components, but it is Q symmetric, so there are only 6. Okay, I can give you the definition of the spin connection, but maybe it will not help you. What I can tell you is this. So if you want practically to compute it, you will do the same as if you want to compute practically a Christoffel symbol, which is that you are going to say, okay, the only thing that I want to know is that this satisfies the Leibniz rule. And in this context, this means that if you look at the exterior derivative of EA, okay, we'll write what is EA, it is a form, plus this guy with the exterior product of E. This is 0. So EA is the one form. So it is simply EA mu x mu. And it's the same going on for omega. So omega omega AB is simply omega mu AB dx dx mu. Okay, and so you lower and get up the Greek indexes with G, and you lower and get up the Latin indexes with eta, with the Minkowski matrix. Okay, so and this is so if you want to compute a Christoffel symbol, what you do is that you check something such that the gradient of G is 0, well, the covariant the gradient of G is 0, and this is how you get your Christoffel symbol. Here, this is the same. Okay, so now if you want to, so why is it covariant? That's a question. D mu, because D mu is well constructed, and it is constructed in such a way that if you change your matrix bundle E, it will change D in a right way. And then so if you do, if you replace E mu A with E prime mu A, okay, we said this replaced by the Lorentz transform. So this was L A. Then you will replace D mu with D prime mu. And in such a way that if you look at D prime mu and you try to make it commute with your group representation for the Dirac spinor, this will actually become U of L. I was yes, and so if you plug this into the Dirac equation, this will tell you this. You will have the same type of phenomenon that will arise in the flat case. This is that if you know you want to compute this gamma prime. Okay, so if you change E into E prime, you will also change gamma into gamma prime because they were defined thanks to the matrix of E. Sorry, d mu prime of U of L U. Okay. So this, with what I've told you, this is just no. So this gamma prime will change as in the flat case, so it will change into I U of L gamma mu because you are just changing the group. And -1. Okay. And then you have d prime u, so you can reverse it, and so this becomes u of L u, and so you find that actually you solve this guy u of L gamma u. And so if you have that in one referential you had u that satisfies the Dirac equation, then in your new differential, so the one that will satisfy your Dirac equation will be so you have still to multiply by your change of basis in C4. Okay, so it is covariant in this sense. So it is not covariant in the sense the equation does not change at all. It changes up to a matrix. But when you change the referential, so if you change at each point the tangent space thanks to a Lorentz transform, you will find that actually you will still get a solution to the Dirac equation, but you will have to change the basis of C4 everywhere. Okay. Okay. Okay, so this is what happens in a. And so as I told you, if you want to know dispersion in the flat case, what you do is that you put up to the square and you retrieve the Klein-Gordon or the wave equation, and then you're happy because you know a lot of things about the Klein-Gordon and wave equation. And here, if you put it to the square, you will find something a little bit more unpleasant, but still manageable, which is if you put the equation to the square. So you find some D'Alembertian. Okay, I will write everything down because this is of course the covariant derivative with regard of the spinor vector blah blah, but okay, I will write it down explicitly. Plus M, so this plays the role of the D'Alembertian. M2U plus 1/4, and then you have a part that is linked to the curvature. This is a scalar curvature. So somehow it resembles a Klein-Gordon equation. So this plays, this is actually box, but in a spin for a spin, and but it is not the scalar box. Okay. So what you do, so d mu is still the same. It is the one that I have defined above, and d mu. So it has to apply to a spinor, but it is not only a spinor because it has this mu part. So it is also a vector. And so how does it apply? So if you look at, so this is of course the covariant derivative for this type of object, and so if you want to see what it does this. So it is which is a spinor, so which has values in C. So you have oh, yes. Find this. So you have a part that is due, that considers the spinorial part, which is just d mu, but you have a part that considers the vectorial part, which is minus the Christoffel symbol. Minus the Christoffel symbol, lambda mu of A. Okay, so it has multiple aspects. And so it is not exactly the scalar d'Alembertian. Okay, it is a spin real d'Alembertian. Okay, so when I refer to this equation, no, I will refer to spin Klein-Gordon or spin wave, depending on the value of m. So if m is 0, this is what I call spin wave, and m is not 0, what I call spin wave. Okay, so now I will tell you my hypothesis about asymptotic. That manifold. So I will consider a matrix G that actually decouples time and space. I'm taking the physicist notation, so we'll have minus h. I will have 1. So h is Riemannian and does not depend on t. Okay, so it decouples. So, and indeed, the Dirac equation, when you take such a manifold, is such a matrix. It is indeed decoupling time and space. So you can consider it as an initial value problem, etc., etc. And for H, I will take something which is close to the identity and smooth. So I will take something of this form. So we'll ask that at each point, so for some choice of coordinates. So at each point, you have this guy, so this should be less than some constant term x to the power -1, so a little bit smaller than x to the power -1. And when you're considering derivatives of h, then I just mean normal derivatives, I mean usual derivative, PD derivatives of h, you will find that it is less than some constant times x to the power -j -1 minus sigma, and this is for j up to the third order. So I need 3 derivatives of h. Okay, so this is what I will take as a manifold. So now, if I consider what I can say with this is that actually, if I look at what happens on the different quantities, so if I look at what is the difference between the covariant derivative and the normal and the usual derivative, I will find that this is actually some field which is bounded, and which is bounded by x to the power -2 minus sigma. And I can also say something about the derivative of this field, etc., etc. And of course, you can say the same about the scalar curvature. So it will be bounded like something like x to the power -3 minus sigma. Okay. And what I mean by this is that no, if you consider either Dirac or spin KG or wave, they're actually a perturbation of the flat. Dirac. Oh no, sorry, this is not. No, yes. Oh no, sorry, I do not mean spin, I mean curved TG. Okay, and okay, but still it is a little bit difficult to say to say stuff about stuff for KG or waves in a curve space, in a curve context. So However, what we can say, however, there exist results of dispersion for the curved Klein-Gordon of the curved waves. And what is good is that now, if I look at the Dirac, if I put the Dirac equation to the square, so I want to look at this equation. So this actually can be rewritten in this way. So this becomes this. So minus the Laplacian H Q plus minus is equal 0. So if I do some algebra, I can find it this way. So this is actually the scalar Laplacian. And G, so I forget to say what was BG, but BG is simply this guy. So this was minus, so it was I omega J AB. This guy. So we have J, which is okay, some complicated writing in BJ. I'll try to make it. But what I insist on this is that actually those two guys, they are not so horrible because okay, they take a long time to write, but actually they are very nice. Behave. They are smooth because of the hypothesis on the manifold, and they are also so FJ. And they are also asymptotically flat in the sense that they decrease a lot as they go to infinity. So in some sense, no, I have an equation that really, so I have a spinorial equation, but that closely resembles to a scalar equation. Okay, I have one part which is a scalar Klein-Gordon of waves and some part which is the perturbation. And so I hope that I can say the exact same stuff as it is possible to say in the non-spinorial. Yeah, we just state the result. Okay, so I will state the result in the case that when you put to the square, you get the wave equation. Of course, we have a result in the Klein-Gordon case. Okay, so we take the Lorentzian manifold with spin structure. Okay, asymptotically flat. Okay, so we have a Strichartz estimate, which is written this way. So if you take U, a solution to the Dirac equation with initial datum U node, so you have the following. You can compute U, the norm of U in LP, and then into some Sobolev space. and say that it is controlled by the initial problem. So the numbers here are related to what happens. So it is exactly the same as in the flats scenario. So it is so they are related by the scaling law that happens into the flats and into the flat space time. So this means that so when m is equal to 0, they should be related in the following way. So you should have 1 over p plus 1 over r, which is equal to 1/2. And then S is actually, so the regularity is actually 1 over 2 plus 1 over R minus 1 over P. So we don't have the endpoint, but this is typical of Strichartz, of Dirac equation, sorry. Okay, so they are not so what does it so what is it? So this is just the Sobolev spaces, but they are adapted to the manifold that we are considering. So they are adapted to the Riemannian manifold, which is driven by H. So what does it mean? So this does just encompass dispersion. It's just that instead of having punctual dispersion, you have to see it in a global in an average over time way. So you're averaging here in T, and then you can find some decay. And what do I want to say more? So yes, so the thing is that in general, so it is not always true that you can have a punctual dispersion. So if you're looking at some exact time, you will see some decay in time. This is not always the case, so there are counterexamples. In this case, I don't know if it fails or not, but we use the technique that we really use the perturbative techniques, which did not allow to prove some punctual decay. Okay, but I don't claim that it does not work. So in particular, we did not assume that G was solving some equation, that it had some structure. I assume that if you ask that G satisfies the Einstein equation, then perhaps you can use vector fields to get some punctual decay. But here, this is absolutely not what we did. So we just use the fact that it was asymptotically flat, and so we perturbed the equation, and then Strichartz estimates that are written. So dispersion estimates that are written in this form, they are very robust with regard to perturbation. So this is why it was not so bad. Okay. So so let me say a few words about perspective. So we would wonder if this type of estimate would be yeah, okay. So what does it serve also to solve some semi-linear equation, and also understand the behavior at infinity. So this type of dispersion estimate, we would wonder if they work in black holes. And so for this, I think we ask ourselves, would they work in asymptotically hyperbolic manifolds? So I think this is the case, but still, for the moment, I don't know how to prove it. I think that if you have a black hole, then you can use the structure of the equation of the Einstein equation, then to say some more, but we didn't try anymore. And then so if you forget about the curved aspect, so then you have some scaling for the Dirac equation, which is the same as the wave equation. And so you can hope also, so for the formation of singularity, you can hope to say something about self-similarity. I must say that also for the Dirac equation, and in particular for the solar model, that is a type of radial Dirac equation, there has been work by Saïd Komek, Cuevas Maraverland. There is a large number of people, Kidis and Saxena, who studied solitons. So this also exists. But the first time I've seen solitons, I think it was working by Esteban Levin and Serre. And also I want to add, so this is for formation of singularity. And for general relativity, I must say that there is a system that I do not see such studied in in the mathematics literature, at least, which is the Einstein-Dirac system, which tells you how a spin 1/2 particle will behave in the context, will change the gravity. And so, as you can imagine, so this to me, so I know only work by Finster, Smollet, and Yo, and by Simona Rotondari. And so this equation is, of course, the Einstein equation with the stress energy tensor that depends on the Dirac spinor that solves the Dirac equation in curved space-time. It's a quadratic semi-linear, non-linearity. So we can also work on the Dirac equation if you're coming from general relativity. And I will stop here.